Okay, let's summarize what you just learned so far about an SN2 reaction. All right. First one, mechanism. What's the mechanism look like? Backside attack. You always think about backside attack when you do a SN2 reaction. A nucleophile approach at the electrophilic center from the direction that opposite from the direction of the leaving group. Okay, we call it a backside attack. And now the energy diagram, I haven't talked a lot about it, but you have seen before that you're gonna see look like a curve, like right there, one curve, one hump. All right, because this is a one-step reaction. Add a nucleophile onto a substrate. It happened right away. One step happened, no two step, no three step. Okay, so since an SN2 reaction occur in one step, we call this type of reaction a concerted reaction. Happen in one step. That's the meaning of it. Okay, one hump is a concerted reaction. You see one hump there, and the other type of reaction you're gonna see 2, 3 humps. Those are not concerted. We call stepwise reaction. We get there later. All right. Now the rate of equation. All right. So it's a bimolecular reaction, which is suggests that there is a collision between the two substrates. All right, and we propose hypothesize that, and the structure of alkyl halide play a big role in terms of the rate of an SN2 reaction. Tertiary blocks the backside attack. Right, the smaller the better. Methyl alkyl halide is the best. Primary alkyl halide is the most common one. Secondary it does, but it's slower, but it still do. Tertiary never do it, and also the vinyl alkyl halide never do reaction. Okay, because too high electron density on the pi electrons, and the stereochemistry will be inversion of configuration. That's because the backside attack push everything to the other side. All right. Okay, just a little bit of why. Some people usually ask me, why does SN2 not do a front side attack? Okay, here's the reason. So they use a molecular orbital theory, which is another like valence bond theory, but different theory. But anyway, to use molecular orbital theory to explain it. So according to molecular orbital theory, a covalent bond will form when a HOMO nucleophile. HOMO stands for highest occupied molecular orbital. The electrons at HOMO level, which is the most reactive in the nucleophile, we do the reaction, which is a lone pair basically, to lowest unoccupied molecular orbital of the electrophile, the most unstable molecular orbital of electrophile, right? So it's a bond will form when electron in a HOMO of the nucleophile goes to LUMO of the electrophile, basically. All right, let's take a look. So there's a HOMO of the nucleophile. All right, so basically the most reactive lone pair in the molecule attack the LUMO of the electrophile. This is a LUMO of the electrophile, looks like that. So we have if you look at the color, right, I color differently. So we have up phase and down phase, or whatever, like plus phase, negative phase, minus phase, whatever they call it. All right, so you can see that this phase and this phase are different. Okay, so HOMO of the nucleophile, we add it onto the LUMO of the electrophile. Now, why? How come? This guy doesn't go from the front. Here's the reason. There's a node right here, which means there's no overlapping at the front side. Only back side you can overlap. You see the same color, they can overlap. Different color, they cannot overlap there. All right. So the nucleophile cannot overlap anywhere that has node or different color. Basically, that's what I want to say. Too high electron density at the front, right? Because bromine, a leaving group, or whatever, the good leaving group, they have some electron density around it. And this guy usually electronegative atoms, right? Bromine, chlorine, iodine, sulfate group, the whole group there, they have high electron density. So the nucleophile won't get in there from the front. Too high repulsion, electron repulsion. Okay, so there's a reason why in an SN2 reaction, a nucleophile never approaches from the front side, always the backside attack, right? Because wide open at the backside, no electrons there. All right, so finish with an SN2 reaction. These two scientists were Dr. Ingo and Dr. Hughes, also come across other substitution reaction. And here's the thing though, when you put these two together, we have sodium bromide, we have third butyl iodide. This is substitution reaction, of course, right? If you look at right here, so bromine replaces iodine, right, on bond to the third butyl group, look like that, right? But this reaction doesn't go on SN2. They'll go back to do experiment, and they all experiment totally different, some of them opposite of the characteristic of an SN2 reaction. Let's take a look at the next video. Okay.